Welcome to Abaqus tutorials. Today we'll be studying how to perform model dynamics and direct time integration. I want to show you, Lifu is going to show us how model dynamics can be a very powerful tool to solve a problem in a very computationally efficient way. And so we're going to study the wind problem subject to gust wind and then determine the response with damping and without damping. With that said, thank you, Lifu. Take it over and show us how to do this in Abaqus. Appreciate it, Lifu.
Thank you, Professor Goyao, and welcome everyone to another Fun Element tutorial. And today we are going to discuss how do we do model dynamics. What is model dynamics and how does it work compared to, for example, directly integration method. So we started with the previous problem that we applied the nonlinear geometry. We applied a nonlinear, non-uniform pressure to the wing geometry. And here are the problem statement before. This is a non-uniform distribution we applied in the previous project. And now we're going to apply, assuming that during the working stage, we have a certain job of the lifting force, which is even for all the surfaces. And the sudden job is 20%, and the frequency for that is 3 pi, so 10 hertz. If you see it in a very long period, this is more like this is similar to a sudden impulse to the entire wing. Since this is we are focusing on the transient response and the steady state response for this problem, this is a dynamic problem. So we are going to compare different methods and different models we have. So first task here is we're going to compare the model dynamics versus the direct time integration. So as you have learned from class, direct time integration is mainly looping method in the time domain, while model dynamics, you're calculating the result as combinations of different modes from different mode shapes. And second thing, we're going to apply the damping to the mode, and we're going to compare the transient response with mode and without the mode. And the simulation time, we can make it longer, make it 1.5 seconds or even more. So the force we are going to apply is like this. Between 0.1 and 0.433, you should have a formula in this form. And otherwise, it will just be 1. So it looks like this. And this function is going to multiply to the function we already have for the non-uniform distributed load. So first of all, we are going to create this function. So the easiest way to create it, I think, is from the Microsoft Excel. So we create a time vector in column A, 0 for time 0, and the start time is 1. So let's do 0.1. And time increment, let's do 0.01. Sorry, time increment, so 0.1 plus 0.01, 0.11. So now select this 2 and then drag this one all the way to 43. Actually 42. Actually, okay, so it ends at you can see that the force ends at 43, 0.433. So after 44, everything is 1. So we can delete all of that and directly enter 1 here. Now let's compute the function. Initially, let's just this should be 1 and start from 0.1. It's still 1, but we enter the formula, which is 1 minus 0.2 times sine 3 times pi, so which is 3.1415296, and then multiply by sorry, this number minus 1, minus 0.1. So now drag the formula all the way to 4 here. And make this number equals to 1 and also 1 here. This is the plot we're going to have. We can plot it here in Excel. So if you plot it, it will look like this. Or yes. So we are going to use this as the inputting table for Abaqus. Now let's move to Abaqus setting parts. This is an Abaqus problem we had before with a non-uniform distributed load. If you check the load, it should look like this. We can delete this one. This is the uniform one. So it has bottom set up. So let's reselect the graph. So I think last time the problem is I delete the sets. So we are going to reassign this force again. And even if you didn't delete this, you need to reassign. And I'll tell you the reason. So this is for the leading edge bolt. You need to click this button, create surface. So we are going to save this set of surface so it's easier to apply later. Let's call it leading bolt. So leading bolts should be everything before. If you go back and check the force distribution, it should be everything before 0.2. So select 2 block of that at the bottom, which is negative y-axis, and down, brown. Everything is the same, just leave it there first. And then leading top. So create a surface, call it leading top, and select the top leading edge of that. Select the brown. Now the bolt tail of the bottom surface, call it tail bolt. Sorry, you don't need to select one. Just create one. And then select all other surface at the tail. Make sure to do this step. It will make your following settings easier. Brown. And then we need a top tail. Sorry. So call this tail top. Sorry. You should start from 0.3. If you select wrong thing, just hold control and select everything that that is wrong, then it can deselect those things. Okay. So this is what we have in the previous project. And today we're going to apply the different amplitude for that. So to do it, first go to step. Remember previously we turned this nonlinear geometry on, and it's a static general one. Now we create a dynamic. So call it direct time integration. So make it after this pressure analysis, and then select the dynamic implicit. And the time, simulation time we're going to do is 0.8 seconds. And then here in the increment, you can choose fixed, but I would suggest automatic. So with automatic, the increment of time will not be decided, and it will based on whether your model is converging or not. Since we're doing nonlinear analysis, it will be much easier to converge if you select the automatic. So let's do give them more steps, 300 step. This is the upper limit. It doesn't need to have, for example, between 0 and 0.8, it has 300 steps. This doesn't mean that. This is just a maximum. You can set it to be a large number, whatever large number you want, or for example, 200. And this initial increment, let's set it 0.1. And minimum, just make it small enough, 1e minus 6. And better to be 0.01 actually, or 0.05. Just make it as small as possible. And then, okay, then click OK here. And in the outputs, in the field output, to save space, we don't need that much thing. What we only need, we just need displacement and stress. And then we are going to set a history output here. Or actually, we can do this later. So, yeah, let's do this. Let me think about this. Yeah, we can set a history output here. So create a history output, call it direct time integration. So to do history output, you need to select a set of node to output the history output. We're going to output this point, the history output from this point. So let's close it first. So to do that, in the tools set, create, and call it like a leading edge tip. So choose node here, and then choose the most leftmost node for that, which is right at the coordinate center. So now we can output history. Call it direct time integration. And choose set here, and then choose the leading edge tip, and then change the increment to be 1. And then we are going to output mainly displacement here. So, and mainly U2 actually. So vertical displacement. And then just to save time, we can, well, it's up to you. You can change it to can change it to something. Well, this actually is not useful, so we can directly delete that. That is not that useful, so we can suppress it. And then now we are going to make changes to the load. To do it in your step, you can see that all this force will be propagated to your second step. So that means originally it's 1 all the way for the second step. And now we are going to minus 0.2 of this function. So we don't care about the first one. We only care about the second part. In your amplitude, here, create a new row, call it this value equals to this value minus 1. So the 1 part is what we get from the previous step, and whatever left, whatever left is what we're going to apply to Abaqus function. So now to do it here in the amplitude, if you see it, it's in the field, and then it's right under the field, and then right click the amplitude, create, call it applied amplitude. Choose the first one, tabular, and then select the step time. Don't forget this is step time, it's not total time. And then we copy the time first to the first row. And then we copy the amplitude here to the second row. So here is what you have. To double check your amplitude, you can go to your plugins tools, and you should have an amplitude plotter here. So you can directly plot it. It should look like this if you make it correct. All the way goes to -2. That is what we're going to apply for the second step. So now go back and keep everything you have, and this is the initial condition for your problem. Now we're going to call it leading bolt 2 or direct. So mechanical pressure, and now we are going to choose the surface we create. Did I save the surface? I think I have this surface. Oh, sorry, I have this name filter, that's why. So this is the leading bolt surface. And make sure leading bolt, region leading bolt, name is also leading bolt, and double check your region is leading bolt. And the distribution, again, we select the lower leading, and magnitude should be the same as what we had before, which is, if you're following the one we have, 10667.6. We can copy this one. And the main thing here is in the amplitude, we choose the amplitude we just created. And that's it. Now you can see that it only be created in the at the second step. So do the same thing for the rest. Leading top, direct integration, and leading top, upper leading, magnitude, paste, and then choose the amplitude. create tailbot direct integration, tailbot lower tail, and this is the paste amplitude. Create a tail top direct integration, and tail top should be upper rest amplitude. So double check the region. This should be leading bolt. This should be upper leading. This should be tail bolt. This should be tail top. So when everything is done, another thing I want to mention here is this mesh may be too fine for your analysis. I just make it fine for better demonstration. So if your storage is not allowed, then you can always decrease the mesh by assigning a coarser seed edge. So once it's done, you can go here and create new job. Let's delete all those ones. So it should have, we have this before, but we are going to create a new one so that we won't mess up with the name. So create new one, call it direct time integration. So now you can use parallelize multiprocessor. I have 4 core in my computer, so I can use 2 here just to make it faster. And then now we can submit our job. Okay. You can monitor until the first step start running, then we can move on to change the model. That is a faster way since your computer can run multiple jobs at the same time. When one of the job is running, you can set up the model for the next one. It won't affect your previous job, but you need to make sure that this job was running correctly. Otherwise, you need to remake the model again. Now you can see the first one is running, so we can move on to the next one. So for next one, we are going to apply the modal analysis for this. One thing you need to know is for modal analysis, it will based on the base state. So whatever stress we applied for the first step will not be shown in the model dynamics. In another word, it means in model dynamics, what we need to do, let's hide this direct time integration first. What we need to do is we apply the pre-stress, and then we calculate the mode shape and the natural frequencies, and we apply modal dynamics. The result for the modal dynamics should be should plus the result for the pre-stress to form the total solution. So, and we will do it using Excel, and you're going to see how do we do it. So let's create first mode extraction. So similar to the previous project, in linear perturbation, we select frequencies here, and lenses, now we do probably 10 mode, and then then everything is the same as the previous project. Now, after the model, you can see that mode extraction is after the pre-stress. Now we create a new one, modal dynamics. So it should be after mode extraction. So in linear perturbation, if you already have the mode extraction, this selection will show up. If you don't have a mode extraction or frequency step, you won't see this modal dynamics. So in modal dynamics, the time we are going to simulate is 0.8 seconds. And the time increment, we make it fine enough, 0.01. Modal dynamics usually will be way faster than the direct time integration. So you can make time increments small enough here. So this will give you 80 steps, right? So we are not going to apply pressure here. Let's include it. Well, it should be the same, but it would be better if you remember to do this one. But for this specific problem, no matter which one you choose, it should be the same because there's no extra step between the mode extraction and the modal dynamics. And make sure that this is 0.8. Everything is done. Now in the field output, modal dynamics, we need to change something. We're not going to output strain, force, or velocity, or even velocity. We just need a displacement and stress, same as previously. And also change this to every one increment. Because we only have 80 increments. It's not a big change. Everything leave it the same. And then in the history output, and we can suppress this one, but we need to create a new one first. Call it modal dynamics. Same here, select the set, select the leading edge tip, change the increment to be 1 per frame. And then what we only interested at is U2. Then we can suppress the original time integration. And once it's done, we go to the loading step. Loading step is exactly the same. You can see that whatever we created for the direct time integration will automatically be suppressed. So create a load for that, call it leading bolt modal dynamics. Choose leading bolt, choose lower leading, same amplitude, same magnitude. And then create leading top modal dynamics. Modal dynamics. And leading top upper leading amplitude. Tail bolt modal dynamics. Tail bolt lower rest, same amplitude. Always check that this, you assign the distribution here and also the amplitude here. And then create the tail top modal dynamics. Tail top, same amplitude here. Choose the upper rest and then amplitude. So it should look the same as your static load. The only difference is a time dependent load. And leave everything the same. Now in the job, we create a new one, modal dynamics. And well, we can use multiple processor here. I want to leave at least one of the processor. So I'm not going to use parallel computing here. I just use one core because model dynamics usually is faster. Now we can submit the second one. If you look at the monitor here, you can compare this two. So it already finished the direct time integration. Sorry, it's still running the direct time integration, and it's all the way at 1 here. Now it's trying to start from 1.05 and then keep on increasing the time. And you can see that here, we apply the load at 1.1. So there will be load here, and then this step starts not converging and vibrating, and that's why it has this response. It will keep doing. Fortunately, we only stop at 1.8. Otherwise, it will take longer to finish. Always remember when you're doing direct time integration, try to use the parallel computing. That will make your result much faster. And for model dynamic, we're still in step 1, which is applying the preload. And let's wait until the model finished. Okay, now the problem is finished. You can see that in model dynamics, we have way more increments than the direct time integration, but it actually finished almost the same time. So let's see how does the result look like. Sorry. So show the results for direct time integration first. And this is a result. We can use this tool to add a new viewport and then put in parallel. In the first one, we are going to open this direct time integration. And for the second one, go to the job. And then we are going to open the model dynamics. So we can link these two together and then give them a view. Sorry, let's do XZ. And then move to a good angle of that. And then let's use edge free. Now we can decouple them. Let's see the first one. This is the direct time integration. And you can see the step time here. Before step time equals to 1, this is the pre-pressure. This is what we have for the previous project, the deformation. Let's use U2. And then start from this one is the dynamic implicit or direct time integration part. You can see that before at 0.5, it start vibrating. The geometry start vibrating. That's because the introducing of the sudden drop. And we can now plot the grade from the history output. We have this history output plot here, and you can see the step. This is like a sine wave, but before 0.1, which is the time we apply the load, is just a constant of with the previous load, and then it start vibrating. And because the direct time integration, we put a very coarse number for that. So you can see the step is also pretty coarse from this one to this one. It's not smooth enough, but it's fine since we don't need to be that accurate about this. And we're going to compare with model dynamics. So for model dynamics, let's do this one, U and U2. So for model dynamics, up to here, step time one, this is the preload stage, which is the same as the direct time integration. And then we do a model analysis. Base state, this is the first natural frequencies and the mode shape, second natural frequency, mode shape, and so on, which is the same as what we have seen in the previous project, and all the way to 10. Now, from here is the model dynamics part. You can see that although the deformation is kept, but the amplitude shows here is 0. So because it takes the model with the preload as the base mode, and everything is added on to it. So whatever we have here is assuming that the initial displacement is 0. So to fully comparing this two later, we're going to use Excel and add up all the values by these initial values here. So let's see. At before 0.1 is just keep zeros, and start from 0.1 is start vibrating, but I think the sudden vibrating is not correct. Let me double check the model. Oh, sorry. I spent a little bit of time to check the model. The model is okay. The reason for the sudden change is because of the Abaqus plotting problem. So in the option command, you can see that we have a deformation scaling factor here. By changing this factor, the deformation will change. So you can see that here and here, they have actually different scaling factor. That's why you see this sudden change. So we are going to make it uniform and make it probably just 5. So now you will see a smooth vibration for this deformation. And to further prove it, sorry, let me delete this one. So to further prove it, you can create the XY data here from the history output, and then select the last one, which is the history output we just created for the model dynamics, and then plots. And choose this one and then plot. And you see that, sorry, let's choose this one and plot again. You can see that these two are, well, the coordinate system is a little bit weird here, but can I move it? No, but we're going to output this to Excel to compare, so it's fine. You can see that the chain for this two is the same, other than model dynamics is more smooth compared to direct time integration. The reason for that is, well, we use smaller time increment for model dynamics, but model dynamics definitely is way faster than the direct time integration. And direct time integration needs more steps to converge. And another thing you can see that is different is the initial value. For, as I said, model dynamics is add-on to the base state. So it won't show the base state here. So although you have an initial value of 0.55 or something, it won't show in the model dynamics. So to fully compare this two, you need to add the initial state to the result. So to do that, let's open the first one and copy the first two columns here. In Excel, we can directly copy and paste. This is for your model dynamics. Notice the time. Sorry, let's delete this plot. Notice the time increment is not uniform for direct time integration. That's what we set. And just to make it faster. And then we copy the model dynamics too here. Hold Shift and Control C, Control V here. Okay, this is the model dynamics. You can see that initial value is 0. So, and the time, although the total time is the same, but the length of the time vector is not the same. So we're going to add all this number with the initial state value, which is this one. So it's equals to this plus 0.546839. So do this to all the numbers. And that is going to be compared to the direct time integration. So we can copy, right click, select this paste values. Delete this line. Now select this two, insert plot here. And here we're going to add another series. So the first one, let's rename it as model. Sorry, the first one should be direct time integration. And then we're going to add another one, call it model dynamics. So the first X data should be all the way to here. And the Y data should be all the way to here. So go back and see your result. You can see that, can I enlarge it? Yeah. So here, let's change a maximum X coordinate to be 1.8. And then minimum, let's change it to 1. You can see that these two are almost the same. And the reason they're a little bit offset is because our time increment is not fine enough. If you make it fine enough, they should be exactly the same. If you only see the dots, actually the dots should be pretty close to each other. And that is a comparison between model dynamics and direct time integration. And model dynamics definitely is much more efficient than the direct time integration in this case, especially for complex structures. But the complicated part for model dynamics is you don't know how much mode. It depends on your applied force. The selection of the modes can be very important too. So now, since we are already select the model dynamics as our reference, let's close this window. And then now we are going to compare model dynamics with dampings and without damping. We already have the model dynamics with without the damping. The only thing we need to change here is following the instruction, change it from 0.8 to 1.5. Since model dynamics is pretty fast, so actually we can do it to 2.5. And time increment, we can just leave it a little bit larger, 0.02. And then without damping here, and then this is your first model dynamics. And let's do this. Create a new one. Let's create a new one. I don't want to erase it. 可以 model without damping. Now we can use parallel computing module processor. I'll use 2 here just to make it faster. So submit. So while it's running, we can go back. Sorry, let's wait until the first step pop up. That means the first step runs through smoothly, and then we can start changing the model. So I received from students about when they're running models, they have several questions. Some of them are related to the saving of your hard drive or something. So to do, it will pop up an information like you cannot change your file or something like that. So the way to fix it is you can delete your ODB file in the folder. ODB file is the result file and it takes most of the space. So if you delete the ODB file, the rest should be fine. You can save your project CAE file and JNL file. Those two are the most important file you have. So once this is start running, let's go back and step is a very quick change. Go to the model dynamics in the damping. Now we say use direct damping data. It has 3 different type of damping. For example, composite damping and Rayleigh damping. And we are going to use the direct damping model now. So direct damping, it can select the start damping mode and the end damping mode. We have in total 10 modes. So we apply the same damping coefficient to all the modes. We apply a relatively larger 5% damping to this model. It's relatively large, but because we are simulating a very short time, so I just want to show you quickly about the damping effects. And everything is fine. Go to your job, create a new job, model with damping. Sorry, the name is wrong here, but it's fine. So we can also use parallel computing here, and then we can submit. This is mode without damping and with damping. Keep monitoring. Oh, this is model dynamics. Keep monitoring the procedure to make sure that nothing has happened. So something you can take a look is first is the error message. If it's get aborted, the error message will show you a lot of things. Second thing is the warning. Usually warning represents something that probably you didn't set it correct, but Abaqus can correct for you. For example, this S4R, since this is a shell element, well, it has the some selection point doesn't have output, so it's get removed, which will not affect our results, so it's fine. And yeah, that is about sometimes self-checking your model, whether your model is correct or not. And now it goes to the second step. Okay, let's wait until it finished. Okay, so the result is finished. Now let's see the results. Create a new one and then 2 of them. And at the wheel point 2, let's show the with them without damping. And at the viewpoint 3, let's show, sorry, viewpoint 2 should be without damping. Viewpoint 3 should be with damping. And well, we can directly see the time domain, probably it will be better. So in the XY data manager, we can create a new one. From the history output, choose the last one we have. Choose this viewpoint, sorry. And then I think it's plot to the wrong viewpoint, but it doesn't matter. Let's see here. This one should be with damping. Where's the with damping one? This one is with damping. Okay, so let's do it again. This one is without damping, and then so let's plot it. So you can see that without damping, 2.5 seconds is like this. It keep doing like a vibration, and the frequency for that should be affected by your impulse frequency and also the natural frequency. And then here, let's plot, create a new one from history output, and then the last one. This one. Sorry. So this is with the damping. You can see that with the damping, this has clearly a decay in the damping, in the behavior. And well, for 2.5 seconds, oh, it started at 1, so this is 2.5 seconds. For 2.5 seconds, it still haven't reached steady state yet. It's still a pretty large vibration, but it's already small enough compared to the without damping case. This is how we apply damping to different mode. Well, we can even apply different damping to different mode. For example, some higher mode in dynamics probably will have higher damping compared to fundamental mode. So this is how we do modal dynamics in Abaqus. Hope that this video will help you in solving your project problem. And thank you for listening to this presentation.